Hello, my name is Timo Kuosmanen. I'm professor of economics at the University of Turku in Finland. And in this talk, I will describe incentive regulation of electricity distribution. So I will start by a motivation why one should be interested in regulation of electricity distribution in Finland. Then I briefly discuss the theory of yardstick competition and its version, the conditional yardstick. Then I'll briefly describe the implementation here in Finland. And towards the end of the presentation, I also go to a little bit more technical details. I'll describe some new methodological innovations for the ongoing regulation period. So firstly, why the energy regulation in Finland is interesting. We currently have the lowest energy prices in the EU. So here is this bar chart from the Eurostat. I indicated with the red arrow Finland, which is on the rightmost of the EU countries. And I take particularly non-household consumers, which means the firms, because of course electricity prices are important for the competitiveness of the companies as well as attracting for investment. So we have recently attracted a lot of particularly data center investments. So we have companies such as Google and Microsoft building data centers in Finland, attracted by the low energy prices, and also TikTok is building a data center in Kouvola. And also we have a very high degree of renewable power in Finland, and also the security of supply is at high rate. So how is this kind of examples of success in electricity markets then possible? So this relates to the series of competitive market reforms that took place already in the early 1990s. Particularly, there was established a competitive Nord Pool energy exchange in Nordic countries, starting from Norway and Sweden, and Finland was the third country to join this Nordic market. So that meant also that to have this kind of competitive electricity generation where firms and households they can freely purchase their electric power from whatever supplier. It also at the same time meant that there's kind of local monopolies in transmission and distribution had to be regulated to have a level playing field for the electricity generation. So we have currently a large number of suppliers in electricity generations, both renewable and conventional energy. But then, of course, this energy need to somehow supply it from this generation to the final customers. And to that end, there exists in Finland we have one national monopoly in transmission. So it is the second part with high voltage transmission. And then we have currently 77 local monopolies in distribution. So this is this between high voltage transmission and the final consumer. We have 77 companies that take care of the distribution. And these distribution companies is particularly the focus of my research and also focus of my talk today, because then this possibility that we have so many distribution monopolies opens up some possibilities for the regulation. So if you think about how this the cost of electricity is then shared, so the share of transmission is actually relatively small, something close to 5% of the total cost of electricity. But in some places, the cost of distribution can be more than 50%. So it's very important that this distribution is organized efficiently. And I should say also that about the ownership that we have many privately owned, for example, pension funds owning this kind of distribution assets, but then also some local municipalities. So what can we do when we have so large number, 77 local monopolies? So there exists this interesting idea that coming from Andres Leifer's article back in 1985, which he terms the yardstick competition. So the basic idea is that when we have many similar firms, we can force them to compete with each other in terms of the cost. So of course, these distribution firms, they do not really face any real market competition. However, the regulator can then force these distribution companies to compete in terms of their costs. And this is the basic idea of the yardstick competition. So Schleifer also describes that of course it's unrealistic to assume that these companies would be identical. And indeed, we have some very large and we have also very small companies in this distribution sector. So Schleifer already proposes that to control for the heterogeneity of these kind of regulated companies, then the regulator could run a regression analysis or regressing the costs on characteristics that determine diversity. So I underlined this line from Schleifer's paper here. So in terms of the regression and costs, then let me go to the Finnish case. So this slide I described the cost frontier model used in Finland. So this is this type of regression model that Schleifer was also talking about. So on the left-hand side, we have the variable input. That is the controllable operational expenditure of these distribution companies. And it depends on the fixed capital K. And then we have three output variables. There is energy supply, network length, and number of use points. So of course the energy supply is this kind of primary output, but then the distribution companies need to also build for potential demand and then also be able to supply when there is some kind of demand peaks. So that's why also the number of use points and network length are used as this kind of output capacity type measures. Then we have also an undesirable output denoted by B. This is those outages. And then we can also introduce environmental variables or contextual variables. And in the regulation model, there is this Z variable is defined as the ratio of connection points to the use points. So that nicely describes the uh, urban versus more rural operating environment. So one thing about this model, you might notice that we do not have the usual error term epsilon, but we have there U and V. U refers to inefficiency, and V is the noise term. So we are not particularly interested in this estimating this inefficiency U. However, we take this kind of possibility into account that firms might also operate inefficiently. After all, they do not face any real market competition. Another point is you might notice also that we have as a dependent variable the controllable operational expenditure. So that represents variable cost in terms of economics. And then we take fixed input capital stock as an explanatory variable. So this is somewhat unconventional in these types of regulation models. So that's why we use this term conditional yardstick competition in this paper by myself and Andy Johnson that we published in the Energy Journal a few years ago. So let me briefly explain how this conditional yardstick differs from this usual type of yardstick competition in the electricity distribution. So there has been this kind of debate that is it better to use operational expenditures, OPEX, or should we have total expenditures, TOTEX in the regulation? So of course, if we apply this kind of total expenditures, then we also have this kind of control for the capital input in this yardstick. However, the Finnish regulator has always been very reluctant to take this kind of TOTEX-based norm to include the capital. So they want to attract or encourage the distribution companies to invest in capital. So therefore, this conditional yardstick was this sort of compromise between this kind of purely OPEX-based norm and TOTEX norm. So in that sense, when we control for the capital input, so the capital also does matter. However, we do not want to discourage the companies from investing. So further details and arguments you can find in this article in the Energy Journal that I cite on the bottom of this slide. But how do we implement then this type of regulation regime? So in practice, here in Finland, we have regulation. Each regulation period is 4 years long, and I should add that this kind of methodology, so this kind of yardstick competition, is fixed for two consecutive periods, so 8 years. So every 8 years, the regulator can update and improve the methodology, but during the 8 year period, the methodology is fixed so that the companies know how they are regulated. So before each of these 4 year regulation periods, then the regulator estimates this cost frontier model that I just presented on the previous slide. So they use empirical data for the preceding 8 year period for which the data is available. So the estimation of the model is based on historical data of 8 years. But then during when this regulation period starts, so then these kind of yardsticks are calculated using these observed values of outputs and bad output and capital during this during the each year. But then this cost norm is then used based on this historically estimated cost model the cost frontier model that I described. So during the regulation period, the regulator doesn't estimate anything; it just calculates these yardsticks. But beginning of each regulation period, the regulator estimates the model and basically estimates this cost function. Okay, and then during this regulation period, the regulator calculates so-called surplus, can be also deficit, but surplus by comparing the actual revenue that the companies charge from their customers and then the so-called revenue cap, which sets this kind of acceptable level of the revenue. And we can think about this revenue two parts. So there is this kind of variable cost part and fixed cost part. So the red part that I have highlighted here, so this is this comparing this controllable operational expenditure, the actual CapEx versus the cost norm that we calculate based on this cost frontier model. So these are variable costs in euros. So what is actually spent and what is this kind of considered to be efficient level of cost. Another part is the capital stock. So because then there is this kind of similar comparison for the actual return on capital, and then the regulator also calculates or estimates the opportunity cost of capital using the capital asset pricing model or CAPM. So then this means that if the companies can operate with the lower operational cost than what the cost norm suggests, then they can be compensated by higher return on capital, so they can get higher profits. So this gives this kind of profit-based incentive for the companies to try to operate in a cost-efficient manner. So this kind of surplus is calculated every year and then added up during this 4 year regulation period. So if a regulated company makes any surplus during a regulation period, then during the next 4 year period, it needs to adjust it, so to speak, pay back to the customers by, for example, lowering their tariffs. On the other hand, if the company makes deficit during the 4 year regulation period, then they can cover up the deficit by raising tariffs and generating more revenue during the next 4 year period. So this is how the incentive mechanism works in this kind of yardstick regime. So let me then go a little bit to this technical matters, and firstly I want to highlight this the fact that the frontier, the cost frontier, that's the cost function C and this effect of the Z variables, that its main interest. And this is something that I see that in the international literature on energy regulation, it's often missed. So many papers are focused really on this efficiency scores, in some sense like even obsessed about the efficiency scores. And indeed, in Finland also the regulation started in 2005, and for the first 10 years it was based on this kind of cost efficiency improvement targets and efficiency scores. But since 2016, We have moved we don't care anymore about the efficiency scores. We care about estimating the cost frontier in euros. And my argument is that from a statistical point of view, it's much more sound to estimate the cost frontier because you can average out noise rather than have this kind of firm specific efficiency scores for which in the noisy setting consistent estimation is not possible even in principle. So that's something that I find very important, and it's often missed in this kind of academic papers on energy regulation. So then let me, towards the end of the presentation, then describe some new methodological innovations that we haven't really published yet in academic journals, but I hope that we manage to publish in the next few years. So when we were planning for the current regulation period that started in 2024, and remember that this methodology is fixed for the two periods, so until 2031, some of the new innovations that we introduced are listed here. So we introduced the out-of-sample prediction error testing for model specification. Then we also took into use weight restrictions to alleviate overfitting. I'll explain shortly what does it mean. And thirdly, we also introduced a control variable to alleviate endogeneity. So we use the energy loss percentage in this role, but this is a little bit too long story for me to describe in this presentation, so I'll leave it for another talk sometime later. But I'll describe this first tool briefly. Okay. So how do we test the out-of-sample prediction error? So notice that, in fact, we are dealing here with the prediction problem. So remember that the regulator uses historical data from the previous 8-year period and then uses that in the following 4-year regulation period. So in that sense, our task really is to try to use this historical data to predict what is the cost frontier in the next 4-year period. So it's kind of a prediction problem, like in machine learning literature. So in a similar fashion, we want to mimic this kind of mechanism when we estimate the model. So we divided our observed data to a training set and a test set. So we use this training set to estimate this cost frontier model, and then we can use the test set in a similar fashion as the regulator does. But because we have then this kind of observed data also for the test set, we can then measure what is the out of sample prediction error. And we mainly rely on the root mean squared error as the criterion that describes how well our predictions are able to fit this cost actual observed costs. Okay. So when we did this kind of out of sample prediction error, we noticed that in these kind of non-parametric estimation techniques that we have used so far, namely convex non-parametric least squares or CNLS, um, in CNLS, we always get very good empirical fit in sample. So the model fits the data really well. So the root mean squared error is about 2000 in this training set. However, when we try to then predict out of sample, we find that the predictive power was actually quite catastrophic. So the root mean squared error out of sample was close to 72 million. So totally like different order of magnitude. So this has been an issue that has been discussed in the recent literature on convex regression. So let me here go to the little bit more technical details. So here is the standard formulation that we use in this context. So this is from this Korsman and Johnson article in the Energy Journal. Energy Journal. So in fact we use the panel data like I described above. So this looks like the first regression equation looks very similar to the usual kind of regression models. Now we have this kind of error term that includes both the inefficiency and noise terms that I described. So in fact, this is can be seen as a semi-non-parametric model. So we have a parametric part with the z variables, and then we have a system of equations with this non-parametric part. So we parameterize this kind of non-parametric part with these coefficients gamma and beta. So these gammas and betas, they characterize a piecewise linear cost function that can be used to represent this kind of true but unknown functional form for the cost function. So further details you can find in my previous publications. So how do we then can try to alleviate overfitting? So one possibility is to then impose some additional penalty terms. So notice here now this objective function changes. So we still have this sum of squares of the error terms epsilon, but then we also introduce an additional penalty for those gammas and betas. So this is so-called L2 norm penalty. Another approach is to then work with the constraints. Mazumder et al. In their article, they describe this kind of Lipschitz norm-based constraints. So that also similarly decreases the variability of those gammas and betas. So in both of these previous approaches, in fact, the idea is to constrain these coefficients gamma and beta closer towards zero. But from economic point of view, we don't really want these coefficients of outputs and inputs to be close to zero. In fact, we want them to have like more like a relevant range. So we don't want them to be very close to zero, but we also don't want them to be extremely large. So therefore, we borrow this kind of idea from the data development analysis literature, where this kind of weight restrictions have been used before. And we introduce this kind of constraints that we put some upper bound and lower bound in these constraints. And how do we set these kind of constraints? Well, we can of course empirically estimate this unconstrained model. So basically, we start from the standard CNLS formulation and estimate the model. So then we get some kind of empirical distribution of these gamma and beta parameters. Notice that these gammas and betas are not constant, but they differ across these firms and across years. So we get some empirical distribution for these gammas and betas, and then our idea with these weight restrictions is we then take the deciles of this empirical distribution. So we basically cut off the lowest 10% and the highest 10% of the empirical distribution by imposing these kind of constraints, and then we solve the model again with these kind of additional constraints. Okay. So how does it improve? And if we then run these alternative approaches with this same idea with the training set and test set to test which of these actually predicts better. So now we see that, of course, in this training set, so in-sample fit is always best with the standard CNLS. So whatever additional constraints or additional penalties we introduce, the in-sample fit will slightly deteriorate. But we see huge benefit in the out-of-sample predictive power. So when we use it for the prediction in the next 4-year period, so any of these techniques have a dramatic decrease in the out-of-sample prediction error. And interestingly, also this weight restricted approach. So this is the bottom part. We see particularly that we get the lowest out of sample prediction error, and also the cost in terms of the empirical fit in the in sample is also not very large. So based on this insight, we then have recommended to the Finnish energy regulator to introduce this kind of weight restrictions that cut off the top and bottom deciles of the empirical distributions of shadow prices to improve the out of sample predictions. And this is also already implemented since 2024. So I'm ready to conclude. So the Finnish Energy Authority uses very advanced incentive schemes based on the conditional yardstick competition to regulate local electricity distribution firms. And I would claim that this is at least one big part also why the electricity prices in Finland are among the lowest in Europe currently. And we haven't stopped this kind of innovations to these previous publications. So in my talk, I also presented some new innovations that are currently already implemented in the Finnish regulation. And interestingly, we are just now in the process of publishing some of these kind of works in academic journals. Some of these papers we haven't even written yet. So there is some interesting stuff coming out also. So here's a couple of references if you're interested in further reading. So for the computational aspects, we recently published this kind of Python package that can do the computations for this type of modeling. And here is the reference to a paper in the Journal of Statistical Software that documents this Python code. I also cited this paper in the Energy Journal that describes the conditional yardstick competition. And finally, here is also a working paper where we discuss this overfit reduction in convex regression, so similar techniques that I described towards the end of my presentation. So if you have questions or comments, feel free to drop me an email. Here's my email address. And if you enjoyed my video talk, here's also the YouTube channel that where I have also other research presentations and teaching materials. Thank you very much. Bye bye.